So to quickly introduce myself, I am a software engineer at Uber, and my team and I are working on building a reliable and scalable Kafka and Flink platform as a service for all the engineers at Uber. Okay, I think So this is today's agenda. First, I will walk through the high-level architecture of Uber's real-time data platform, including a few key components. Then we will dive into why Protobuf is important for us and how it fits into Uber's overall architecture. I will next discuss the solutions we developed, and by the end, we will summarize the key takeaways for this journey and outline the next steps in our Protobuf support strategy. As many of you know, Uber's business is in real-time by nature. So when riders request a ride, they would want to get on the road as quickly as possible. And the drivers want to take as many rides as possible to maximize their time and earnings. And the real-time data platform is crucial for Uber's architecture. That enables the swift response, ensures that seamless user experience, and support Uber's data-driven decision-making. So let's take a look at Uber's real-time data platform, which actually includes three main components: streaming data, which is built on top of Apache Kafka, and the streaming processing platform built on top of Apache Flink. The real-time analytics platform built on top of Apache Pinot. So they are considered as a critical infrastructure at Uber, and we are using them in Uber's core business flow. So the data lake ingestion is typically considered as a batch processing. It is listed here because in this talk we will also touch briefly on data lake ingestion. Okay, next, let's have a closer look into those components. Streaming data platform, which is built on top of Apache Kafka. It is being considered as the cornerstone of Uber's tech stack. It serves as the foundation for both real-time data and the batch system. Kafka is used for various purposes, including the pops-up communication between the microservices, streaming processing, log ingestion, and data lake ingestion, etc. But Uber's architecture is somewhat unique in the industry, especially for the pops-up use cases. We implemented two proxy layers, a producer proxy and a consumer proxy, specifically designed for microservice pops-up use cases. So the communication between the microservice and the Kafka is handled by the proxy layer through the RPC protocol instead of the native Kafka protocol. It is a self-service platform, so the engineers at Uber can create topics through the CLI or UI by themselves. More than 1,000 services at Uber use Kafka, and we provide two languages, Java and Go. So as of today, it processes more than 17 trillion messages per day and 10 petabytes. So my colleagues has a talk 6 months ago. At that time, it's just 7 petabytes, and now it's more than 10. So it goes really quick. Since Uber operates in real time, producer latency is crucial to our business. And we support 10 millisecond P99 producer latency even for the lossless clusters. So the next is the streaming processing platform built on top of Apache Flink. Flink has been used for various purposes at Uber, including the real-time notification, the monitoring, alerting, fraud detection, and more. And somehow the slides just fast forward. And so we are also considering use Flink for the data lake ingestion recently. It is also a self-service platform. So the engineers can just create the job by themselves. We offer two distinct Flink options: the Java-based microservice solution, which allows users to fully utilize the powerful streaming analytics capability of Flink, and a SQL-based solution, which makes writing a Flink job really easy. The data freshness is in terms of seconds, and we are processing trillions of messages per day. So the last part is the real-time analytics platform built on top of Apache Pinot. It has been used for a variety of purposes as well. So it supports low latency analytical queries over terabytes of data. And we have various of product teams build their customized dashboard on Pinot to virtualize and exporting important metrics. And from the ingestion part, user can onboard the tables through a user-friendly UI. And it also supports both online and offline data stores. And the query part is through a Presto-like service. Actually, last part is a very important piece for this talk, is our schema registry. So the schema registry is developed in-house at Uber and serves as the source of truth for all analytical schemas. So it also is a self-serve platform. And we provide both backward and forward compatibility for the schema registry. And we are doing the validation for all the schema changes. We have more than 1,000 services use the schema registry at Uber, and it supports more than 1,000 QPS. Okay, here is a few real-world use cases for our real-time data platform. It includes the rider and driver matching. So all the supply and demand data flow into Kafka and then goes into our in-house search engine, then powers our driver and rider matching. And the heat map data in the application is powered by the Flink, while our hourly earning metrics is powered by Pinot. So this is just a few examples. There are many more use cases built on top of Uber's real-time data platform. But next, let's take a look at our motivation and why we need to build the Protobuf support for our real-time data platform. So when talking about Protobuf, we cannot avoid to compare it with Apache Arrow. There are many differences between these two formats. And in general, Arrow is commonly used in the big data stack, while Protobuf is frequently used in the service-to-service communication, especially combined with the gRPC. The Arrow is more self-describing, and the Arrow schema is in terms of JSON format, make it easy to pass between different services, and ensures that each service has the information it needs to interpret the data correctly. While Protobuf is quite opposite. It relies on the external defined proto files. And we need to use the ProtoC compiler to generate the class and file descriptor set, and then share it across different services. So both Arrow and Protobuf support backward and forward compatibility, but also in different ways. Arrow supports changes like adding fields with default value, renaming fields, and promoting the types. And it still can maintain the compatibility. Well, since the schema travels through with the data, and the old and new versions of the data can still be interpreted correctly for different services. Protobuf, on the other hand, it uses a tag number to identify the field. So it can make the encoding really compact. But on the other hand, it really relies on the proto files and all the generated class to interpret the format correctly. And if, let's say, you change the tag number in the proto files, then it might mess up the decoding. But on the other hand, Protobuf is more forgiving compared to the Arrow, in that it allows the unknown field to be ignored during the deserialization, which reduces the likelihood of decoding failure. However, the problem is that it also lead to some data quality issue. But still, from the performance wide, it's known that Protobuf is faster compared to Arrow. Well, sorry, my slides sometimes like flipping around, and probably because of I have wrong setup with my slides. Yeah. Okay. So in general, still that Arrow is like more fit for the data stack compared to Protobuf. But why we need to support it? We have a real problem to solve. So the problem we are facing is the data format discrepancy for our online microservices who uses Protobuf for the communication and the data stack that only support Arrow. So it requires someone to translate the Protobuf format into Arrow format. So it's like we have two people speak different languages, and then we need the interpreters to translate between them. So just a note here that Kafka itself does not have any specific data format. So data can be stored as Protobuf, Arrow, or JSON, but the rest of the data stack, such as Flink, especially Flink SQL, Pinot, and Ingestion, do not support Protobuf at Uber previously. Okay, this is a real-world use case. We have a service called Fulfillment. It's an extremely critical service at Uber. It uses Protobuf internally, and it writes a Protobuf encoded data directly into Kafka. So this data is crucial for the downstream. So the downstream services want to use Flink SQL to filter, enrich the data, and they also want to use Pinot to create a dashboard. But because of the fact that those stack does not support Protobuf in the past, so we have to create a Flink job manually to convert the Protobuf encoded data into Arrow. Well, this is a manual effort, so it's like quite troublesome with the more like topic onboarded, right? Every time we onboard new topic, we need to create a new Flink job for this. And also, we often evolve the schema. And when the Protobuf schema starts to evolve, we need to manually update the Arrow schema and also update the conversion logic. Well, this will cause like the schema get diverged over the time. And also, this additional layer increases the storage cost, plus it impacts data freshness. So initially, we consider, how about let's just solve this problem at one shot? So the data platform all use in-house libraries to decode the data. What if we can convert Protobuf to the Arrow on the while? This can help us solve our problems. And we actually tried this route. So we convert the Protobuf to Arrow on the while, and we build an in-house library. So this solution is considered as scalable from product's perspective because we managed to make everything controlled in the platform team. So for the product teams, they only need to go to our UI, onboard this topic, and enable the Protobuf to Arrow conversion. But this solution comes with some problems. First of all, as you might aware, like Uber's data platform runs in a high scale and high throughput. And this conversion is actually quite slow compared to both Arrow and Protobuf decoding. So it will impact the throughput for the high throughput use cases. And also, the schema's evolution is not fully guaranteed. User can break the compatibility, which often isn't discovered until the schema gets updated. And also, we build an in-house library, which need us to maintain. And it doesn't solve another problem. It's that, in fact, many services use Protobuf internally, right? But they don't take a route, let's write the Protobuf into Kafka directly, because we have a library available for the Arrow. So what they did is they write their in-service conversion logic to convert the Protobuf object into the Arrow object. Actually, many services take this route. So it means like those engineers, they are like application or service developers. They do not familiar with the big data stack, but they need to learn the Arrow data format. They need to implement the Protobuf to Arrow conversion logic, and they also need to manage the Avro schema continuously. It might not be a very big effort for one person, but our footprint is like we have thousands of services using the Avro. That means like it impacts probably at least thousands of engineers. Plus, the Protobuf to Avro in-service conversion does come with the performance penalties. So a few months ago, as a customer just showed me a frame graph where like the Avro encoding part take like 30% of the CPU cycle for that service. So we want to solve this problem as well. So therefore, we come up with our final solution, which is to provide a native Protobuf support in our real-time data stack. We believe this is the right decision for us to go in the long term for a few reasons. First of all, Protobuf and gRPC is kind of the de facto standard for services at Uber to do the communication. So supporting Protobuf along with Uber's strategy. And also, like as indicated by the many industry benchmark, Protobuf is faster compared to Avro. So from the microservice perspective, they are able to get some efficiency gain. Lastly, with Protobuf get more and more popular in the industry, communities also worked on Protobuf support for many open source technologies, which can be leveraged so that we don't need to write everything from scratch. Next part, we are going to go through our architecture. So our main focus will be the schema management, and then I will also touch briefly on our platform integration. Let's examine a few constraints that actually highly influence our design. So the first part, as I said, we already use Protobuf at Uber heavily. So we have a Git repository used to store all the Protobuf files for the microservice. We call it IDL registry. And then another part is, so in our existing schema registry design, we have topic to schema 1.1 mapping, and they are essentially use the same name. And it's really difficult for us to change that. While the different topics can share the same Protobuf message type. Lastly, we have many high-throughput platforms that will require us to optimize for the performance. Okay, because of the first constraint, so we end up with two sources of truth for our Protobuf schemas. So microservices will use IDL registry as a source of truth, while the schema service will serve as a source of truth for all the data schemas. So, but we have to do something between these two layers. Therefore, we come up with a solution that we still treat the IDL registry as a source of truth for all the Protobuf files, while we build the integration between the data schema registry and the IDL registry to ensure that the Protobuf schema are seamlessly synced into the data schema registry. We also want to consider the user experience. In order to simplify the user flow, the integration is designed to be straightforward. Users only need to provide the IDL file path and the Protobuf message type when they do the registration. And then the platform will handle the rest of the heavy lifting. And the data schema management layer will be handle the schema registration, the compatibility validation, the schema evolution, and also expose a library for the data platform for integration. Okay, in the previous slides, we mentioned we have a single source of truth for all the Protobuf files, right? Well, this is actually a simplified explanation. In reality, the flow is slightly complex at Uber. So at Uber, we use monorepos, and we have one for each language. So we actually have 4 monorepos. And typically, engineers make schema change in monorepo instead of IDL registry directly. And then we have a sync job to sync the schema from the monorepo into the IDL registry. But for the registration purposes, we still can consider the IDL registry as the source of truth for all the Protobuf messages. And also, we can safely assume that Protobuf imports will be available in the IDL registry, which means we are able to run the ProtoC compiler to compile the file descriptor set and the generated class correctly. Lastly, we safely assume that IDL change is not very frequent, so that at this moment, we don't need to handle the scalability issue. We can start with some naive solution for the schema registration and evolution. With that, we come with our solution, which is we only allow register on the IDL registry. And when user registers the schema from the UI, a backend API will be called, which will be responsible for compile the file descriptor set, generated Java file, and also it will jar the Java class and put it into remote storage, later being used for the platform integration. Well, registration is first part. We're still going to evolve the schema. So although we end up storing the Protobuf schema in the IDL registry and the data schema registry, we want to avoid the hassle of requiring engineer to update both places. In order to streamline this, schema evolution in data schema registry will be happen automatically right after the diff get landed into the IDL registry. Automation is wonderful, but it also introduces a risk, such as the schema compatibility issue. Additionally, because Protobuf supports the type reuse, and it's very common that when you change one type, it could impact a large number of the schema. So we want to keep close eyes on it. So to prevent all those risks, we implement the pre-land validation in the monorepo. As I said before, engineers actually land the change into the monorepo. Once the change gets landed and synced into the IDL registry, we will run the post-land job to update the schema. The process will be very similar to the schema registration. Schema get evolved, of course, the version going to get bumped. And let's have some brief concept on how the schema gets stored in the schema registry first. So the data schema here, we are referring to the Protobuf message type. And internally, we call it top-level message. So we run the ProtoC compiler during the registration, and we store the full file descriptor set into our database. And the same proto message type can be reused by different schemas. We actually evolve those schemas separately, and each of them will have its own version. And if you have any embedded messages or imports, they will not have its own version. But of course, when you change those embedded messages, we will still do the schema evolution behind the scene, and it will result in the version bump. So here I have an example, right? We have a message type called person, and inside the person there is an embedded message called address. So this message type gets used by two schemas, full and bar. So probably because the full get registered earlier than bar, so the full is in version 2 and bar is in version 1. And we actually have a separate table to put the analysis on the Protobuf message type to the schema mapping. So in this table, we not only store the top-level message, we will also store all the embedded messages. So you can see here we have two rows. The first one is person, which gets used by full and bar, and also address, which is used by full and bar. Why we need this? Actually, let's take a look how the schema evolution going to look like. So when we land the change, we do a risk analysis during the pre-land validation, and we also do the gradual schema update in the post-land job. Let's check out the example here. So we add a new field called city into the address type. So in the pre-land validation, we are able to know that the address type get updated. So we scan the table on the right. So we know that we might need to run a compatibility check for full and bar. And also, assuming this type get used by 1,000 schemas, then we definitely want to put a reviewer, an expert to take a closer look. And once the change get landed, right, we will still use this table to analyze how many schema get changed and then update the schema accordingly. So we are able to do the controlled sequence update because each schema actually has its separate version. And we can start with bumping up the version for the least important schemas. Okay. Next, we will briefly touch through the platform integration. So when we're talking about platform integration, we also have a few key requirements. So first of all, we want this to be transparent to our users. Well, the data producers still need to know what is the schema type they use. The data producer actually should not even need to care about it. And also, performance is important. The integration should achieve optimal performance for the high throughput use cases. So why am I mentioning this? It's because Protobuf has two ways to decode messages. Either use the dynamic message or the code gen. And in general, code gen is faster to dynamic message. And also reliability is important for us. So we come up with our three solutions. We want to reuse our existing user interface, make everything transparent. We want to adopt a code gen as much as possible. And we are doing the schema compatibility validation to make sure the reliability. So we already talked about the validation in the previous slides. So here we are going to focus on the rest two, which is reduce the existing user interface and the content generation. So this actually comes to our milestone one scope, which is the managed platform that our team owns. It includes the Pinot and Athena-X, which is our Flink SQL platform. Why we are focusing on these two parts is because these two are fully managed service, and we are responsible for encoding and decoding data for the users. So we have the full control, and also if we don't support it, user cannot use it. So for the Flink part, Uber's Flink SQL is deeply integrated with Uber's infrastructure. It will help you to discover Kafka cluster automatically. And also it's a simplified version. It only have one source table and one sink table and a SQL query that connect them together. So user can just write a very simple Slack query. Well, in the end of Slack, the data synced into the destination. So to integrate Protobuf into this kind of architecture, what we need to do is we need to map the Protobuf schema into the Flink table schema. We need to convert the Protobuf object into raw data, and then we can because we can have the raw data to, let's say, Protobuf or our output based on the schema type, right? So actually, the underlying schema type does not really matter for the user. So we adopted the code generation for the performance optimization. But because this is a platform, it's like we cannot compile jar every time when we run a job. So we ship the Protobuf jar into the remote storage. And then, when we do a job deployment, the Protobuf jar will be shipped to the Flink task manager as part of the local resource localization. And for the Pinot, we did a similar thing. So we map the Protobuf schema into the Pinot schema. We convert the Protobuf object to the generic row, and we store the jar file in the object store for Pinot to access. Before we start this project, Pinot does not support code generation, and we actually contribute and introduce the code generation support for Pinot. So performance is important. And if you don't run benchmark, you will not know the real performance, right? So we run the benchmark, And our conclusion is that Protobuf with code generation is 4 times faster compared to Arrow and the Protobuf dynamic message. Of course, there are some tricks we need to do because in the process we do find some issue and we have to adjust it. And from users' perspective, everything is transparent. They do not really need to care about the data as in Protobuf format or Arrow format. They can just simply integrate with it. This project actually gives us a lot of benefit. It helps us to increase the developer productivity. It helps us to simplify our architecture, especially for the microservices. The performance gain is probably not too big, but still is useful. And also, as we are doing this, probably as some kind of pioneer in the industry, we are making some good contribution back to the community as well. A few key learnings we have. First one, start early. So if you pay attention to all the schema management part, you might realize that we actually did a lot of effort to accommodate the fact that we have another source of truth for ideal registry. We can avoid this if, let's say, we get started early and where we can help to redirect user or help to shape the user behavior. And also run a performance benchmark. Do not just assume something is faster. There are some configurations could impact the performance. And also try to avoid the deep nested schema, especially the deep nested schema with a lot of options, like optional fields. This will impact performance. This is something we learn and we tune. Lastly, get to know your customer and the use case earlier. So in our process, we made some assumptions like something our user might not do, but in fact they are doing it. So we have to change our design to accommodate it. Okay, so what we have done so far. So the Protobuf support is already in production, and we already have quite a few use cases. So this is very interesting because it's really weird when an infra-team develop a project and the product team start to reach out even before the project gets completed. But this happened to us. We have 2 early adopters on board into production even before we announced the project GA. But we still have a lot more to do in order to make Protobuf fully in parallel with Arrow. And what is our next step? The first one is native data lake ingestion. So right now we are still relying on Protobuf to Arrow converter for the data lake ingestion. And we want to make it fully native so that we can get rid of our Protobuf to Arrow converter. It will make our engineers' life easier. And then next part, this is a little bit interesting. So as I mentioned very earlier in this talk, that Uber's use case for the pops-up messaging use case is slightly different than the industry. So instead of having consumer service consume from Kafka directly, we build a microservice as a proxy layer where pull the message from Kafka and then send it into the downstream consumer services through the gRPC protocol. Well, it's a gRPC protocol, but right now we are still passing through a byte array. And in the next step, we want to just pass through the well-typed Protobuf message to the downstream. This will make our customers' life much easier. So this is actually an open source project. And here is the QR code if you want to check it out. Of course, I cannot do the project on my own, right? We have a lot of team members who help to make this come true. Okay, next, I think that's it for our talk, and I'm open to any question.